you.
Thank you.
Yeah. Mihir? Shivada?
Yes, sir, like she has joined now. I will request her to unmute.
No, maybe you can start the session then.
Okay.
Yeah.
Good evening, everyone. Welcome to the third technical talk of IEEE MTT-S Women in Microwaves Virtual Colloquium by Miss Sadia Farjana ma'am from Chalmers University, Sweden. I now hand over the virtual podium to Dr. Saptarshi Ghosh sir from IIT Indore, the session chair for the session. Over to you, sir.
Good evening, everyone, to Indian participants and other people. Good morning, good afternoon, and good noon to everyone. I believe coming from the other time zones, particularly. And good afternoon, Sadia. I think you are in Sweden, so as of now, the time clock is close to 4 p.m., right? So good afternoon to you, particularly. And thanks for accepting the invitation from the IEEE MTT Kerala section request to join in this wonderful talk series. So this is the third talk series in this series. Particularly, we have already experienced the two wonderful talk series, one in the morning, one in the afternoon, just before this series, and also the introductory session was going good. So Sajia is currently doing PhD in Chalmers, I think. Yeah. So before going to the although let's start with the formal introduction of Sadia Farjana. So she was born in Bangladesh. She received her BSc in Electrical and Electronics Engineering from Chittagong University of Engineering and Technology. She received her MSc degree from Chalmers University of Technology in Microtechnology and currently working towards PhD at the Chalmers University of Technology, Gothenburg, Sweden. Her interests lie in the field of micro and nanosystem technology and fabrication of millimeter wave and sub-millimeter wave components. She has some wonderful publications in the last few years, like particularly one is the micromechanics, one is the Lysentic thesis, I think. So, and I hope that she's going to give a wonderful deliberation talk in today's lecture. So over to Sajia. Thank you. So please start your presentation.
Thank you. So let me share my slides first. So is it working?
Yeah, it is visible, but it will be good if you make it full screen. Yeah, fine.
Okay.
Thank you. Over to you, please.
So hello, everyone. Thank you for giving me the opportunity to talk about my research in this wonderful event. I listened to the previous talk and I was also present in the morning. So when I checked the the participants list, I saw that all the peoples are very experienced and I'm pretty new in this field. But it's good to talk about my research or what we are doing at Chalmers. So I'm currently doing my PhD studies and in the Department of Microtechnology and Nanoscience. And in our lab, Electronic Material and System Laboratory, we are trying to develop a low-cost and straightforward micromachining process to fabricate high-frequency waveguide components, especially for batch fabrication. So based on my research, the topic of today's presentation is micromachining of gap waveguide components for millimeter wave and sub-millimeter wave applications. So I will first briefly present the background, the motivation, why we are doing this type of research. I will also talk about high frequency applications, why we are approaching towards high frequency. And of course, there are challenges. That's everyone who is working on these high frequency waveguide components. We are facing some challenge, and so I will mention very briefly the challenges. I will talk about different types of waveguide concept. And since my research is focused on gap waveguide technology, and I'm not sure about the participants who are, if they're familiar with this gap waveguide technology, because it's comparatively a new technology. So I will discuss about working principle, how this gap waveguide works, and then introducing the challenges at the conventional waveguide manufacturing techniques and why we are working on micromachining, why micromachining is important for these high frequency applications. And finally, I will present the low-cost micromachining methods that we are developing in our group for gap waveguide components. So, Internet of Things. This becomes a very hot topic these days. By Internet of Things, we mean devices connected to each other and connected to the internet. And the number of devices connected to each other and connected to the internet is growing day by day. The present situation is enormous number of connected devices, enormous growth in data traffic, profound impacts on daily lives and social activities of human beings. But the challenge is RF spectrum is already crowded at microwave frequencies. At the same time, there are some wish list that comes from the consumers, which is we want low cost product, compact and smaller wireless modules that we can take or carry everywhere and anywhere, high reliability and best performance, of course, no limit on data rate, and connectivity everywhere. So we can see that there is a contradiction between the present situation and the consumer's wish list. And to get a connectivity everywhere and to control these enormous devices connected to the internet, we see that microwave frequencies are kind of overcrowded. That's why we are approaching towards higher frequencies. So recently, terahertz gap or terahertz region, it becomes a very hot topic, or it's been discussing every now and then. So this terahertz region basically covers 100 gigahertz to 10 terahertz, which covers actually millimeter wave, sub-millimeter wave, and terahertz frequency range. The advantage of this frequency range is larger bandwidth, higher transmission rate, reduced component size, and mostly available spectrum. The application of this frequency range of this terahertz band is enormous. We can use those terahertz frequencies for imaging due to its very good resolution quality. It can actually penetrate through many different materials. So it's been used for spectroscopy to detect hidden objects. It can easily detect the water contents between different tissues. So it's been used for medical application. And since there are like very available bandwidth and higher frequency carrier available, so it offers very high data rate. So it's been used for the communication. But as soon as we move towards higher frequencies, we start to use waveguides to transmit waves. And most commonly used or very known waveguide is hollow waveguide, which is rectangular or circular waveguide that we, the people who are working with these transmission lines, we know that we have this rectangular waveguide and hollow waveguide everywhere in our measurement labs. It's a very established technology. and it offers very low insertion loss. But the challenge actually starts when we approach towards higher frequencies. Because this hollow waveguide needs very good electrical contact and alignment between metal split blocks, it becomes very challenging for the conventional machining method to get this type of electrical contacts and alignments between these metal split blocks, which makes this waveguide technology very complicated and costly. And there is another very known waveguide concept, which is planar transmission line. Which most commonly used planar transmission line is microstrip lines, and we are also familiar with coplanar waveguides. They are very simple to manufacture. They are planar, and it's a very low cost technology. But the problem is, at higher frequencies, it suffers from dielectric material. With this dielectric loss is very high at high frequencies. And also it suffers from conductor loss due to narrow lines on thin substrate. After that, so considering those issues, there has been developed another waveguide, which is substrate integrated waveguide or post-pal waveguide. So instead of connection between two metal plates, this waveguide technology use metal wires to get a connection between these two metal walls. But this waveguide technology is mostly dependent on dielectric material and also suffers from dielectric loss. So there is some issues like the waveguides that can offer low insertion loss becomes very costly and complicated to fabricate. And on the other hand, the waveguides that is very simple to fabricate is suffering from high insertion loss, which is very difficult to use for higher frequencies. So then newly proposed waveguide concept is gap waveguide technology. It's been proposed by Professor Persimmon Kildare in 1988. So he actually proposed this waveguide technology based on hard and soft surface. So what is a soft surface? A soft surface is a corrugated surface which can stop propagating the wave. So if a wave try to propagate in the transverse direction, then it will see some discontinuity in between this ridge line, and then it cannot propagate in this direction. But in the longitudinal direction, this wave can propagate easily. And in this direction, this soft surface acts as a hard surface, which can use to propagate a wave. So this is the main concept of gap waveguide technology. But there are some other concept which is also being used, which is a very basic theory of electromagnetic wave. So if we consider an electric conductors, then electromagnetic wave cannot pass through an electric conductor, but it will reflect. And any electric field that touch an electric conductor must be perpendicular to it. On the other hand, a magnetic field close to an electric field must be parallel to an electric conducting surface. And the rule is completely opposite for a magnetically conducting surface. But it is difficult. Okay, so then if we then from this concept, think about this parallel plate configuration, which is if we bring a electrically conducting surface and magnetically conducting surface parallelly placed to each other, then no wave can propagate through them due to this boundary condition. But it is difficult to get the perfect magnetic conductor in nature. But that can be actually fulfilled by a metamaterial concept. A metamaterial is a surface where like continuous rows of pin can be placed at a certain distance, and the pin heights need to be a quarter wavelength. And then this surface can act as a magnetic surface. Based on this concept, actually, he proposed gap waveguide concept. So if we place a perfect electric conductor and an artificial magnetic surface parallelly placed to each other with a separation difference less than quarter wavelength, then no wave can propagate. But if we put a metal strip in between these two magnetic surface, then wave can propagate only through this strip. So as I mentioned before, this metamaterial surface acts as a artificial magnetic surface, and this pin structure acts as a soft surface. So no wave can propagate through this direction, only propagate through this ridge. The benefit of gap waveguide concept is it doesn't require actually any electrical connection between these two metal plates, because due to the soft surface, there will be no wave leakage. Wave can only propagate through this ridge. So as it doesn't require any electrical connection between the top metal plate and the bottom metal plate, it has manufacturing flexibility. Also, it doesn't require a very strict alignment issue. So the manufacturing is very flexible, easy mechanical assembly and readily packaged. No or very small dielectric loss suffered by this gap waveguide structure, as wave basically propagate through air. Also, it provides very good trade-off between opposing factors, which is low loss and manufacturing flexibility. So in this picture, you can see three different types of gap waveguide. So this is a ridge gap waveguide, where a ridge is placed in between this artificially magnetic surface, and this top metal plate acts as an electric surface. This is a groove gap waveguide. This groove gap waveguide actually acts as a rectangular waveguide, and this is a microstrip gap waveguide. In my research, I mainly focused on ridge gap waveguide and groove gap waveguide. So due to this flexible manufacturing process, or flexibility in the manufacturing process, gap waveguide already managed to have a low cost mass production by injection molding. So in this image, you can see antenna, slot array antenna operating at 30 gigahertz. And if we compare the results with a milled version, we can see the injection molding piece is working similarly as milled pieces. So this can indicate that this gap waveguide technology can be used for very simple and easy manufacturing methods. So this is actually the normal way to manufacture waveguide component is computer numerical control method, which is known as CNC method. So CNC method is a very well established method, very good accuracy at low frequencies. As soon as we move towards higher frequency, it becomes a very expensive method. Feature size and the tolerance required at high frequency applications become too demanding, which is very difficult to handle by these machines. It becomes a very time consuming process also, because it's a serial method, and we can have only one single piece of waveguide component in a single run. So if we consider batch fabrication, this method becomes very expensive. At this now, if we think about micromachining is a process where we fabricate miniaturized pieces especially in micrometer scale or nanometer scale. It becomes very popular for semiconductor industries, microfluidics, sensors, and actuators. So the benefits of using micromachining is they offer feature size and tolerances down to micrometer level. The surface roughness is down to nanometer scale. It can give very high aspect ratio geometries. It has very high alignment accuracies, and volume manufacture is possible. You can fit as many pieces possible in a single run, and you can have the similar number of devices in a single run. It has high product uniformity. because you can fit many pieces in a single run, and all the pieces you get in a single run perform similarly. So it has high product uniformity, which is very important for many applications. Comparatively, it's a low-cost process in high volume. In this image, you can see photoresist patterned with several are very good and well-established process. It doesn't require any high temperature and pressure, and also batch fabrication is possible. On the other hand, leak
I feel like, is there any connectivity issue?
Yes, yes,
I
sir.
also feel the
Yes,
same. Yes.
sir, I think we can tell her to turn off the video. Like,
Yeah,
we
yeah,
can
yeah,
see
yeah.
the-
Yes. Once you hear her, please tell that.
Okay, sir.
Sivada,
Yes, sir.
Sivada, you may write the same thing in chat box.
Sure, sir. Sir, should we call her? Like, her number is there. So,
I think Shibata, it's better to call her because I think she has not now present in this connection.
yes, sir, I will call her.
Yeah, just call her in WhatsApp maybe.
Yes, that will be better, I think.
Yeah.
Can you hear me now?
Yes, Sadia, like I can hear you.
Okay. And
Yes,
I
so
don't know, like when you missed my presentation.
can you open your presentation? It is
Yeah.
not visible as of now.
Yeah. So let me share. Yeah.
Please go on. So, yes, further. I'll- I think slide 17 is the last slide. Slide 17.
Okay.
I hope
Okay.
everyone also agree with me. This is the last slide.
Yeah. Right.
Okay. Sorry for that.
So okay, you start, resume from here with your full screen view. Yeah, thank you.
So I'll start from slide 17.
Yeah, it is not in the full screen view. It will be better for us.
Now.
Make it full screen. Yeah, fine, good.
Okay.
Yes.
Okay, so the most commonly used method to fabricate high frequency waveguide component is silicon based method, thick photoresist based method, Liga method, or diffusion bonding. So due to very short time, I will not explain all the methods, but I will just explain, talk about silicon-based method and thick photoresist-based method. But as you can see, there are some issues with this Liga method and diffusion bonding because they need high temperature and pressure. The production cost is very high for some of them. It requires long processing time also. So this is how we process a silicon wafer. So we, in this image, you can see a 6-inch silicon wafer, and this is of course for a specific processing. So we sputter it with aluminum as a hard mask. We spin a photoresist and then pattern the photoresist. So photoresist is usually a material which is sensitive to um, UV light. So when we pattern the photoresist, we get the required pattern based on the photoresist type. Like for positive photoresist, the unexposed area will cross-linked and the exposed area will dissolve. And for negative photoresist is the opposite. So we pattern the photoresist and then we start deep reactive ion etching to etch through the wafer. And when we remove the aluminum and the remaining resist, we get the pattern. So in this image, you can see the pins and the ridge. And after sputtering and electroplating of the conductive layer, it's ready to use as a waveguide component. So if we consider polymer-based method, SU8 photoresist is most commonly used photoresist for very thick structures. Benefits of using photoresist is it's also a very well-established process as silicon-based method. Batch fabrication is possible. By this method, thick structure is possible to achieve. It can give high aspect ratio structures and comparatively, it's a low-cost process. So this is the processing steps. So the thing is, we need a substrate, and in our case, we use a silicon wafer. We deposit SU8 photoresist and spin coat it. The spinning speed actually determine the layer thicknesses that we need. Then we soft bake it. During the soft baking, the liquid of the photoresist will evaporate and we get a solid surface. And then we expose it. For SU8 photoresist, it's a negative photoresist. So the area that is exposed under UV light will cross-linked and unexposed area will remain unchanged. So during post-exposure bake, this cross-linking process actually occur. And then we can repeat these process steps depending on the steps that are required by the antenna or the waveguide or the filter. So once all the processing, all the layers are defined, we develop the photoresist, and the developer actually remove all the uncross-linked photoresist, and when we release the structure from the substrate, we can have the required chip. And for gap waveguide components, we need to sputter and electroplate it with a conductive layer to make them conductive. So if we consider the silicon micromachining and AC weight micromachining process, we see that it requires many processing steps, long processing time, especially for photoresist method. We need waiting time between each step, which makes the processing time very long. It has low cost efficiency because the number of devices fit in a single wafer depends on the wafer size. And if we consider a high gain antenna, the size of the antenna becomes very big. So we cannot fit many pieces in a single run. So it actually reduces the cost efficiency if we consider the time. It also suffers from geometrical issues. So in this image, you can see some pins which suffers from vertical sidewall issue. And in this image, you can see a bended structure, which is a very common problem for liquid photoresist. So if we want a structure which is very thick, then it suffers from this type of bent structure. Also, this liquid photoresist suffers from edge beat issue, non-uniform radius distribution. So if we consider those type of issues, we actually need a precise microfabrication of high frequency components, which has fewer processing steps, which needs less processing time, and possibly a batch fabrication method and a low cost process, because for some of the application we don't need to think about the cost of the production, but for many application we need to think about the cost, especially if we collaborate with the industries, then it's very important to think about the cost of the fabrication method. So considering those issues, we develop a template based injection molding. So in this template-based injection molding method, it seems very complicated at the beginning, but finally we will see how it works or solve some issues. So first step is we fabricate a master. So a master is a piece where once it is fabricated, it's always stay there and we never remove it from the substrate and from the master. And usually a master contains the accurate or original geometry of the final piece. So once we, from the master, we fabricate a mold. The mold has the reverse structure of the master. So in this image, you can see where there is a hole, we have pins, and where we have pins, we have holes. And by using this mold, we will finally get a final structure by injection molding. So I will explain the process in detail now. So first, to fabricate a master, we choose AC weight photoresist because the antenna that we fabricate, it's for D-band at 140 gigahertz. So the thickness of the layers which is needed is very thick, and only AC weight photoresist can provide this type of thick structure. So we use AC weight photoresist. We repeat the process steps that I mentioned before. Like soft baking, spin coating, soft baking, UV exposure, and you can see during post-exposure bake, we get some area cross-linked and some area unchanged. And when we develop it, we get the final master. By using this master, we fabricate a mold. But before using this master as a mold, we treat it with CHF3 to make the master non-stick. And we use PDMS to fabricate the mold. Once we pour the PDMS in the master, we degas it, and after heat curing, we can easily remove the PDMS mold because the master is already a non-stick material. So in this image, you can see a PDMS mold, how a PDMS mold looks. So it has the opposite structure of the master. And then we design an injection molding process. For injection molding, we use a newly developed photoresist, which is ostomer. The benefit of using ostomer is you can use it at room temperature, and after UV cure, it becomes a stiffy or rubbery structure, and that can be easily released or removed from the substrate. And then when you heat cure it, it will get the final stiffness. So this is how we plan the injection molding process. For injection molding, we use a aluminium mold. So the aluminium mold has two holes. When we place the PDMS mold, previously fabricated PDMS mold, with this aluminium mold, we press them together with a glass plate and clamp them together. And then when we inject the ostomer, we UV cure it and release it, and then after heat curing, we can have this final ostomer chip. So this is the final process steps look. So if we consider the preparing of a master and preparing of a mold, it takes 24 to 28 hours. But the benefit of this thing is this material, the master and the mold, is reusable. And then for the final device fabrication, we need only 2.5 hours from injection molding to the final device fabrication. So based on this method, we fabricate a slot array antenna. So it operates at 140 gigahertz. It has 3 layers, a slot layer, a cavity layer, and a feed layer. So if you want to read more detail about this antenna, you can check the references. So the issue to fabricate this antenna is it's the flatness issue, because it's very thick structure, height of each step, overhang structure. It has an overhang. You can see here we need overhang structure, which is very complicated to get with silicon micromachining or other photoresist based method. And this small step in the transition, it's also very complicated to achieve by other fabrication method. But when we fabricate the slot layer, we can easily transfer the slot layer in a SUEX master, and then transfer it to the mold. And then we have this SUEX, ostomer slot layer. In these two images, you can see a slot layer fabricated by ostomer and slot layer fabricated by SUEX photoresist. And you can see the slot layer fabricated by ostomer is completely flat. Flat, and the SUEX process, SUEX slot layer fabricated by SUEX has a bend. And if you compare the processing time, you can see it's only 2.5 hours to fabricate a slot layer by this injection molding method, whereas to fabricate a slot layer by this SUEX photoresist is very long. Processing time is very long. By following the same method, we fabricate the cavity layer. So the challenge of this cavity layer is it has this hole. To get this hole, we design the aluminium mold in a way that it has some pins. And then when we inject the ostomer, the pin actually create this opening. And here you can see a complete cavity layer. The similar way, we fabricate the feed layer. But for the feed layer, we have only one pin in the middle, which creates this opening for the transition. So the purpose of showing all of these layer is you can design the aluminium mold requiring the geometry and that is needed, and then you can easily transfer the design by combining it with the PDMS mold. So this is the fabricated pieces. the slot layer, the final slot layer, cavity layer, and feed layer. And from the measurement result, you can see the measured input reflection coefficient was below -11 dB over 14% bandwidth. And the measured gain is 31 dBi, which is very good at this frequency range. But when we use this AC weight, we face some issues or the complications. That's why we think about another photoresist, which is dry film photoresist. So the challenge of using liquid photoresist is it's difficult to distribute the resist uniformly. It has age bead issue, which actually affects the final exposure dose. Thick structure suffers from flatness issue. It has very long processing time. But if we consider a dry film photoresist, it can overcome all those issues easily. So the height of the dry film photoresist is not limited to any extent, because you can just laminate one layer after another, and you can get very thick structure. And the sidewall are very straight for these dry film photoresist. I will show you later. Fabrication cost is comparatively low compared to silicon processing. And it also overcomes all those issues that we suffer for when we use liquid photoresist. So this is the process flow of dry film photoresist. Dry film photoresist actually comes in paste combined with two plastic sheets. So we first need to remove the plastic sheet, and we need a substrate. We put the uncovered part in the substrate and then laminate through a normal office laminator. And here you can see a laminated dry film photoresist, the PET sheet on top of it, and you can see that it is very flat, and it's laminated very perfectly. So the processing step is we remove the plastic sheet of one side and laminate it in a substrate. We remove the plastic sheet or the PET sheet of another side, and then we expose it with the required mask. So if you want a dry film substrate, or then you need to flood expose it, otherwise you can just start working with it. And then after the lamination, after the flood exposure, you remove the plastic sheet and start laminating another dry film sheets depending on the thickness that is needed. And then finally you will get the final pattern of your dry film photoresist. So based on this process flow, we demonstrate a ridge gap waveguide resonator by SUEX tri-film photoresist that can operate above 200 gigahertz. If you the required height of the pin was 217 micron, and then from the ACM image you can see the achieved height of the structure is 272 microns, which is actually very good at this frequency range, and the measured surface roughness is very low for this type of structure. From the fabricated result or the measurement result of the fabricated piece, we see it has very good agreement with the simulation results, and the measured Q value is very low and the loss is very low, which shows that dry film photoresist is a promising candidate for high frequency waveguide components. That's why we fabricate some gap waveguide transmission lines by this AC weight photoresist. So the target height was 270 micron, and as you can see, the achieved height was 272 micron. From the measurement result, we see that it has very good agreement with the simulation result. And for the so we actually fabricate three different types of transmission line. And for straight ridge gap waveguide, insertion loss is 0.075. But for the groove gap waveguide, which performs similarly as a rectangular waveguide, is the insertion loss is 0.048 dB per millimeter, which is actually similar as the conventional micromachining methods. So the reason to present the result is we can say that we can use this dry film photoresist to fabricate high frequency waveguide component. The fabrication process is very simple and easy, but it can perform similarly as the very well established micromachining method. To conclude, it's difficult to conclude actually within this short time, but I would say micromachining is the suitable method to fabricate high frequency waveguide components due to its huge benefit over CNC milling method, and the proposed method or the developed method that we developed in our group, which is injection molding of photoresist and dry film photoresist based method, can be used for batch fabrication of gap waveguide components because it is very like the processing time is very low, and also we can have like batch fabrication easily by these methods. Finally, I would like to acknowledge my supervisor, my examiner, and special thanks to all the university collaborators and my funding agencies, and all the university collaborators who showed interest in my work. And thank you, MTT-S, for inviting me. Yeah, thank you for your attention.
Thank you, Sadia Farjana, for this wonderful presentation. We have learned a huge amount of presentation from there regarding the fabrications, regarding this batch fabrication, regarding this fabrication techniques. So let's take a few questions from the participants who have already been given these questions in the chat box. So the first question has been asked by Shivada, a student. The question is that can 3D printing be used to create such gap waveguide structures? Up to what feature size can we accurately fabricate using injection molding? Over to Sadia.
Yeah.
Please.
So it actually depends on which frequency band you are using. So as you know, like as I showed you, like injection molding has been used for 70 gigahertz, but we know the feature size becomes very small above 100 gigahertz. So it becomes very complicated, and also the fabrication accuracies becomes very difficult for injection molding. Injection molding is possible below 100 gigahertz, but above 100 gigahertz, we need to think about something. But this micromachine based injection molding, with these we can have like very high accuracy. So injection molding can be used.
Thank you, Sadia, for the response. So there is another question is from the participant, Ansha KK. So the question is that is it possible to fabricate WR3 waveguide using micromachining technology operating in the terahertz frequency?
Yes, it is possible. It is possible, especially for this dry film method. You can use, you can fabricate actually very thick structure and very thin structures. It depends on the laminator that you have. So if you have a very good laminator that can laminate very thick structures, it is possible to have yeah, very thick structures. And if you go below like very if you go towards very high frequencies, then you can of course get it. It's easily you can get dry film sheets. The thinnest sheet is 10 micron, so you can get 10 micron thick structures by using this dry film also. But you can also order dry film sheets require like the customized thickness, but for research purpose we never order like customized sheets, so we are using the sheets that is available.
Another question has come from the same participant. What is the minimum slot width possible on the WR3 waveguide? So this is probably the last question you're going to take from the participant. So Sadia, if you can comment on this question, what is the minimum slot width possible?
Okay. Minimum slot width, you mean the thickness
I
or?
think the resolution you can think of.
Okay.
Yeah.
The resolution, as I mentioned, I think 10 micron, it's possible.
Okay. Thank you, Sadia.
Yeah.
All the questions. I have one last question from my side.
Yeah.
That the presentation you have shown. So the presentation is a wonderful presentation regarding the fabrication techniques using the microprocessing technology. Now, considering the region 10 community members, particularly the Indians, Bangladesh, there how we are going to implement this concept, citing its high cost and the funding issues. And you all always know that from your country or from your neighbor countries, we are always struggling with the funding issues.
Yeah.
So how the researcher, particularly the young researchers, how they are going to resolve these issues? Any particular suggestion from your side? Yeah. That is my question. If you can comment on that, it will be very good for everyone. Yeah.
Yeah. So your question, can you repeat it again?
Yeah.
So,
So that particularly the microprocessing technology, although the resolution is very good and we can fabricate any high frequency devices, the fabrication cost is on the higher side. I think you have understood that there is a high amount of funding is required to realize those prototypes and obviously measurement and other things. So considering the region 10 community, R10 community, where Indians, Bangladesh and other neighboring countries are there, where the funding issue is always a big challenge for us.
yeah.
So there, how we are going to resolve this thing, or how we are going to accumulate this project, and how we are going to take this project and we are going to work on this project. Or you
Yeah.
have any suggestion how to reduce the cost while you are trying to introduce this concept? Maybe I am like, if my answer question is fine, maybe others can also explain this. I hope that explains
Yeah.
you the.
It's actually, yeah, the micro machining, it's it's like huge cost. We need huge funding, that I know. It's difficult to implement in our country, but the dry film processing that I mentioned, it can be actually run in our country. Like, for this dry film processing, we don't need clean room. We don't need, the only cost is the dry film sheets, which people, it's very new, so people are not using this thing. So when I actually work on this type of project, I also think that maybe people can start working, like people from my country can start working on these type of things. Yeah, but for research purpose, it's very it's very complicated to get a funding, especially when we don't have sufficient labs, like the clean room. We need clean room.
Yes, I
Yeah,
understand.
I would like to comment on this particular query from Dr. Ghosh, and then I have a question to Sadia also. So, firstly, yeah, it's a very costly solution. We need to have a lot of funding to create this kind of facility. But situation actually is not that bad, especially in India. Such type of work is happening in SCL Chandigarh and then SAC Ahmedabad. So there are facilities up to 300, 400 gigahertz. So we have the silicon micromachining technique at SCL Chandigarh. I know some of the people there who are working on W band, V band, and even above 100 gigahertz also. So it is costly, but such solutions are there. And moreover, this type of platform creates the opportunity to collaborate and handshake. So probably nowadays research facilities, of course, challenge, but there are different modes by which probably we can do. So that's what I wanted to add as a comment to session chair, Dr. Ghosh, and also to Sadia. And now I have a technical query to Sadia. I hope we'll be very soon becoming Dr. Sadia and with very high quality work. So you are talking about different kind of fabrication techniques, especially at requiring such high resolution. So there would be different kind of perturbations, different kind of defects, like different kind of micro defects that might appear on the wall, right?
Yeah.
So how do you incorporate those kind of perturbations a priori in your simulation model? For example, there are some kind of theoretical models like Hammersmith model or Bechdel model, Fourier model. So do you consider those kind of models in your simulation or your theoretical analysis, or you directly go for fab?
No, I actually like I don't design particularly, but once I get the design, I actually try to consider some issues like the pin heights. We cannot have the accurate pin heights from the simulation result. So I try to see what can be the effect of this type of error. So yeah, that I do. But we use CST for this type
Okay.
of modeling. Yeah.
Okay.
And
So
the alignment errors that I try to see what can happen.
right. Okay. Okay. Thank you. Over to Dr. Ghosh.
Thank you, Dr. Saha,
Yeah.
for the highlighting or for highlighting those applications also. I also wish that that in the coming days we shall have a good collaborations between that type of external fundings as well as the Indian researchers, so that like all the young researchers, even from the small universities, large universities, they can like collaborate with all the outsider like abroad researchers, and they can work on these exciting projects. I hope that these things will come more and more often in the coming days. Let's see. Yeah. So I hope the presentation is over. So, and if anyone has any comments or any queries, so they can please ask Sadia through the email IDs and through the LinkedIn and other profiles. And as we are almost on the end of the verge of the end of this today's session, I'm requesting the moderator to give the necessary instruction for the photo session. So thank you to everyone for again. Thank you, Sadia, for the nice presentation.
Thank
And
you.
also, yeah, thank you. Thanks a lot. Please, moderators, please please give the instructions.
Thank you so much, ma'am. Now I request all the participants to turn on their video so that we can have a virtual photo shoot.
Meher, have you turned